Okay, reflection, refraction, diffraction, and interference. So what is reflection? Well, it's when a wave strikes an object and bounces off. Notice you have an incident beam and a reflected beam. Also notice that the angle of incidence on this angle right here has to be equal to the angle of reflection. There's a couple of different types of reflection. There's specular reflection and diffuse reflection. This is obviously on a smooth surface and this is on rough surfaces. Specular reflection always ends up with a distinct object, whereas diffuse reflection ends up with many times not an object being able to be seen. So again, the law of reflection just states the angle of incidence equals the angle of reflection. Refraction is the bending of waves when passing from one medium to another. It's caused by a change in speed. Slower, more dense materials will cause light to bend toward the normal. Faster, less dense materials cause the light to bend away from the normal. So I have a little, okay, so I have a little simulation here I want you to look at. What causes the wave to actually bend? Look what happens whenever the wavefront hits the medium. It hits it at an angle. So the wave has a different speed in this medium as it does in this medium. So since this side of the wave hits first, it slows down first, therefore bending the wave. And of course you do, this is a reflected wave. So some of the light will go into the pool and some of it will go out of will reflect off of the surface. Now notice also there's these indexes of refraction, and these are just numbers that help us understand the way an object is going to behave the way that medium is going to behave when light hits it. So for instance, if I move this down to water, you can see that the index of refraction of water is 1.33. The index of refraction of air is 1. You can also go with more of a, let's see here, a ray diagram instead of a wave. Ray diagrams, now notice what happens whenever I move this. Ray diagrams help us understand which way the ray is going to move. Let's see what happens whenever I move this to air. Notice it just goes straight, and there is no reflection. So you can change this a little bit around and get different reflections and refractions. So just understand that. Okay, so moving on. So refraction depends on the speed of light in a medium, the wavelength of the light. Shorter wavelengths, blue, bend a little bit more. So you can see that's what's going on here. So you see that white light is coming in and it's being bent or refracted based on what wavelength that it has, because different wavelengths will travel at different speeds in a medium. And that's why you see this blue. Whenever it hits here, there's refraction, and whenever it hits here, there's refraction. So blue has got a much larger displacement than the red does from where it originally came in at. Okay. So an example of refraction would be whenever you see a fish in the water. The fish is actually here, but it appears over here. And this also happens in the pool, like whenever you're jumping in a swimming pool. That's why you don't jump near people, is because it's not right where you think it might be. Diffraction, the bending of waves around a barrier. Longer wavelengths, like red, bend more, opposite of refraction. So diffraction and refraction, kind of opposite things. Interference. So this is where we get to see waves or light have more of a wave-like tendency, and at the same time we get to see it have more of a particle-like tendency. So what happens here is this is called the double slit experiment. Waves come in, they're all in the same phase, and because they're all in the same phase, you get two different wave fronts, just like water, and you get constructive and destructive interference. Like there's constructive and here's destructive. But what's interesting about this is that if you just let one photon through, which they've been able to replicate this, then it doesn't exhibit this. an actual, like whenever they did this with photographic plates, what they found is that it was just, you saw one bright spot where the light hit in the photographic plate. So rather than seeing this wave-like tendency that you would expect to see, you see just one little bright dot, which is more of a particle-like nature, the photon. Okay, so let's talk about some applications of this. Fiber optics is just whenever you have total internal reflection. It's whenever light is reflected back into the denser medium. Another application is lenses. The incoming parallel rays converge to a single point, and this happens whenever you have a converging lens. And of course, a diverging lens is the incoming rays diverge from a single point. So I bet you've probably seen lenses like this, and you'll be exposed to them fairly soon if you haven't seen them already. Another application is rainbows. This is what happens when you have refraction, reflection, refraction. So at the surface right here, you have refraction occurring. Then at the other side of the rain droplet, you have reflection. Then again at the surface, again, you have refraction, which is again just changing the ray, which way the ray is going based on different indices of refraction. Diffraction grading is glass or plastic made up of many tiny parallel slits. This may also be reflective. Spectroscopes, reflective rainbow stickers, or CD surfaces are all examples of diffraction gratings. Another example would be thin films or bubble and oil slicks. You get to see the interference result, the interference patterns caused from double reflection. So you have reflection here and reflection here, and then you have constructive and destructive interference going on, and that's what creates all those cool little colors on there. So another cool application is blue sky and red sunsets. Molecules in the atmosphere scatter light rays. Shorter wavelengths like blue and violet are scattered more easily. So at noon, there's less atmosphere, less scattering. This gives us blue skies and a yellow sun. In the evening, there's more atmosphere the sunlight has to go through, more scattering, and therefore because the blue gets scattered more easily, that leaves orange and red, and that's why we have an orange-red sky and sunset. Okay, well thank you for watching this video, and I hope it helped you out.